This section will give an introduction to confidence intervals. The learning objectives for this session are to describe how confidence intervals are used to make inferences about population parameters, to calculate the confidence intervals for the mean of a normally distributed population with known standard deviation, and to understand the effects of varying the sample size, the population standard deviation, and the confidence level on the confidence interval. As we discussed in the last module, the value of an estimator observed in a single sample is called a point estimate. If a process is normally distributed, the condition of the process can be fully described if its mean and standard deviation are known. The mean of the process can be estimated from a sample of size n by the sample average x bar, and the process standard deviation can be estimated using the sample standard deviation s. Now, we've seen these equations many times before, and I'll be using them again today. So we also discussed in the last module when we often have to draw conclusions about the quality of a population from the quality observed in a sample. Now, if we can get a large size sample, for example, n equals 50 or greater than 50 from our population, then our estimators x bar and s obtained from the sample can be used as estimates of mu and sigma of the population, respectively. If, however, only a small size sample is available, then the sampling error of the variability in our point estimates x bar and s will be too large to make a good estimation. For these situations, statisticians have derived methods for making inferences about population parameters. And we will discuss two of these inference procedures, confidence intervals and hypothesis testing. So in this session, we're going to talk about the method of creating confidence intervals for population parameters for normally distributed populations. So the point estimate, especially from a small sample, if you remember, it's just one observation of a random variable. Its value will vary from sample to sample, and we cannot trust this individual value to be the true value of the population parameter. So we need to resort to interval estimation, in which we can create an interval around our point estimate, such that there's a certain level of confidence, say 95% or 99% confidence, that the parameter we are seeking lies in this interval. The level of confidence is called 1 minus alpha, and we call the interval a 1 minus alpha % confidence interval, or CI, for the parameter. Now, we're going to use an example from Professor David Gallagher from Virginia Tech. Suppose we are in an orchard which has 20 apple trees, and we place 10 buckets under each tree in order to catch falling apples. If we are interested in the number of apples per bucket, maybe we want to know if we can carry the buckets, we know that the number of apples per bucket for any specific bucket will vary, and we assume that this value will be normally distributed with a mean and standard deviation. So let's look at what happens when we look at just one tree. From the 10 buckets, so our 10 buckets here, we find a sample mean, so x bar, the total of number of apples divided by 10 buckets, to be equal to, in this case, 6 apples per bucket. And we can calculate from our sample tree a standard deviation S of 2.8 apples per bucket. Now, we know that x bar is only from one tree. It is just a point estimate based on the sample for the population mean. Now, if we want to be 95% confident that the mean number of apples per bucket in the entire orchard is within a range based upon our one tree, we can use a confidence interval to define this range. So here's our orchard. What does this mean? We have 20 trees in our orchard. If we take a sample from a particular tree, meaning taking the sample of n equals 10 buckets from that tree to determine the average number of apples per bucket from the population, we can construct a confidence interval for the population mean based on that sample from that, which is a tree. And so we had the example here. We had tree number 1, x bar equals 6. And what we want to do is to create a confidence interval such that from our x bar plus or minus a given constant k, we can be 95%, in this case we had 1 minus alpha equals 95% confident that our true population mean lies within this interval. And we can do this also for tree 2, and for tree 3, and for tree 4, and so forth, all the way until we get to tree 20. For each of these samples, each of these x bars, we can calculate a confidence interval, and we will be 95% sure that the true population mean of apples per bucket in our orchard will lie within these confidence intervals. Now, we have, of course, this limit. We've said that we will only be 95% confident. And since we have 20 trees, what this means is that from 19 out of our 20 trees, which equals 95%, 19 out of the 20 trees will have confidence intervals that contain the true population mean. But because we have a 95% confidence interval, one of those trees, we will find the sample average, we will construct a confidence interval, and that confidence interval will not contain the mean number of apples per bucket for the population.